All right, so I received a question about the sample questions for this 25F30A for the last few topics, and the question was about problem 4 and problem 10, and those I will just discuss here in this video. So please read the problem number 4. There is quite a little bit to read. I will let you do that. Okay, so the way I interpret it is the following way. So I have an object, okay? The distance initially from that object to the lens is d0, or let me call this little d, okay? It's known, it's not given, but it's known, some number. So let me just not denoted by d, okay? The distance to the image, it's said that is capital D. Well, again, some number, okay? Let's assume it's given. So the height of this image is given, so it is capital H, okay? So it's something against a number. And of course, the original, how high the object is itself is also given, H0. It's also something, we don't know it, but something. So this is what we had it initially. So then they said that the distance from the object to the lens was doubled. And this is, I decode this in the following way. So it's 2 times d. D was the initial distance. So it's 2 times d after that, after the distance was changed. So what about the distance to the image? Well, it was said in this problem that it actually became 1/2 of the original one. So it was d, it became 1/2 of that. So what we need to find is we need to find the height of this image. Okay, that's what we need to know. Obviously, the height of this object didn't change because we just moved that. We didn't shrink it or anything. So H0 stayed the same. Okay, very good. So let's go back to our initial part here. So in the initial part, we know that magnification is given by the following equation. So it is H image divided by H object equals, and I here use the absolute values for simplicity, so that not to deal with the signs, etc. So here it is d image divided by d0, and the same as magnification. So from this part, again, so I will only look at the magnitude here. For this part, I can actually write what H, capital H is. Okay, so it's kind of assumed that it's given, but I want to express it in terms of the original height of this object and all these distances. And here, instead of di and d0, I substituted these notations over here. So I obtained this result over here. It's not yet useful, or it's not very useful right now as it's written, but you'll see its utility just in a second. Okay, what about the final situation? For the final situations, we have all of these known quality. So what we need to find is the HI, right? So the height of this image. Again, I use the same equation as over here, but in this case, for this situation, it's a little different, right? The numbers are different. So this part I just rewrote. This is just has to be applied to these givens, all right? So, and here I just substitute instead of distance to the image, I substitute 1/2 of d, 1/2 of d. Instead of distance to the object, I substitute 2d, 2d. Okay, and from here I obtain the following ratio. It's 1/4 capital D divided by little d. Okay, but now let me solve this for what we wanted to solve it for, right? So it's height of this image. So it will be 1/4 d divided by little d times h0 over here, right? So capital D divided by little d times h0. Okay, but in this combination over here, I can immediately recognize this capital H. Yes, this capital H. So let me just rewrite this as 1/4 of capital H, and that's the final result. So that's how this answer is formulated there. Okay, very good. So let's now consider the problem number 10. Please read it first. I will also take a look at it in a second. All right. So what's going on over here? So we have a divergent the divergent mirror. So I draw it over here. Divergent mirror. Okay, so we have an object. This object is distance d0 away. Since the divergent mirror actually can trace all the light rays, so this one will just reflect. So this straight light ray, I have to extend my from the focus, I have to extend this line. This is how it's going to be reflected. So the image, how it will appear where these two light rays cross. The only way for them to cross, I need to draw actually them behind the mirror, right? So, and this is how they will appear for me. So I have to extend the light rays behind the mirror, and this is where they cross. They will just define me where the distance is located, the image is located. Okay, very good. So since here I have to extend something to where the light doesn't really go. Okay, I have to extend this light rays to something imaginary, then the image is virtual. Okay, if its image is virtual, then di is negative. This I'm going to take into account when I substitute into this equation. I took this into account by substituting the minus sign over here. So originally we have 1 over d0 plus 1 over di equals to 1 over f, right? So, but I know that di will be negative, so I will instead here substitute the absolute value, and here we'll take this negative sign into account. Okay, and I'm solving this for the 1 over f for the focal distance. I will get this result for the focal distance. Substitute the numbers right you have, and you'll get this final result for the focal distance. Using this focal distance, it's negative, right? So, which makes sense, it's divergent mirror. So now I can compute the radius for that mirror. It's 2 times focal distance, and I got negative result again. So it makes sense because it is a divergent mirror, right? So the curvature has to be negative. And then we are asked to find the magnitude, so I just disregard this minus sign and I get the final result. And that's it.